Hello guys, today we'll talk about the counting methods applied in counting the number of sample points. Let's dive in. First, let's discuss the MN rule. If a sample space contains n equal probable sample points and an event A contains exactly NA sample points, it's easily seen that the probability of A equals NA over N. Here's a table indicating the number of pairs. As you may see, there are exactly m times n unique pairs. For example, note the unique pair of A1, A2, B2. Object A1 is paired to B2 to make a unique pair. This is called the MN rule, and it's the first thing in combinatorial analysis. The MN rule can be extended to any number of sets. If you have three sets, A1 through AN, B1 to BM, C1 to CP, the number of distinct triplets containing one element from each set is MNP. Here's a practice question. An experiment involves tossing a pair of dice and observing the numbers on the upper faces. Find the number of sample points in S, the sample space for the experiment. Alright, so here's the explanation, or the solution. The first die can result in one of six numbers, 1 through 6. And ditto with the second die, 1 through 6 again. They both have 6 possible outcomes for the faces of the dices, or die. So it's like this table. Hence, via the MN rule, there are 36 unique sample points. What if we want to know the number of ordered arrangements that can be formed? Well, an ordered arrangement of R distinct objects is called a permutation. The number of ways of ordering n distinct objects taken R at a time will be designed by the symbol P and R. And right there you can see the formula for the number of permutations. We're concerned with the number of ways of filling R positions with n distinct objects. In case you don't know about factorials, this is how they work. The exclamation mark denotes a factorial. The factorial means to multiply that number all the way to 1 consecutively. Here's an example of 5 factorial, where it would equal 5 times 4 times 3 times 2 times 1, which will eventually equal 120. Also good to note, 0 factorial equals 1. Here's an example for permutations. The names of 3 employees are to be drawn at random from 30 employees. How many sample points are associated with this experiment? So here's an explanation. We have 30 employees, so n would equal 30. We want to pick 3 employees, which would mean an order of 3. So r would equal 3. So you literally just plug it into the permutations formula as n equals 30, p equals 3. Do some quick math, and your result should be 24,360. So what this means is that there are 24,360 possible pairings of 3 with 30 employees. What if we want to know the number of subsets of various sizes that can be formed by partitioning a set of n distinct objects into k non-overlapping groups? The number of ways partitioning n distinct objects into k distinct groups containing n1, n2, all the way to nk objects, where each object appears in exactly one group, would equal n equals n factorial over n1 subgroup factorial, and so on all the way to nk subgroup factorial. Here's an example. A labor dispute has arisen concerning a distribution of 20 laborers to 4 construction jobs. The first job requires 6 laborers, the second, third, and fourth require 4, 5, and 5 laborers respectively. The dispute arose over an alleged random distribution of the laborers to the jobs that placed all 4 members of a race group on job 1. Determine the number of sample points in the sample space S for this experiment to find the probability of the observed event if it's assumed that the laborers are randomly assigned to jobs. So, the number of ways of assigning 20 laborers into the 4 subgroups is 20 over 6, 4, 5, 5. So as you can see, it's going to be 20 factorial over 6 factorial times 4 factorial times 5 factorial times 5 factorial again, which should equal that really long number, which is roughly a little a little under 10 billion, so 9.77 billion. So, now, with all four ethnic groups, for all four ethnic members going to job 1, the remaining 6 need to be assigned to the remaining jobs. So now that we we put all four ethnic groups into job 1, job 1 should now have 2 job openings. So a new formula accounts for that. So now the total amount of employees now is left is 16 with 2 to job 1. So the answer should be 30 million and change. So the probability of this would be 30 million change over the 9 billion change, which should equal 0.31%. So, if the laborers were randomly assigned, the odds of 4 ethnic workers going to job 1 is 0.31% by chance. So there's reason to doubt that there wasn't some strings being pulled. The number of combinations of n objects taken r at a time is the number of subsets, each of size r, that can be formed from n objects. Those will be denoted by C and R. So, the number of unordered subsets, which is the keyword unordered, unlike the last permutations which are ordered, of size r chosen without replacement from n available objects is the formula below. So CNR equals n factorial over r factorial times n minus r, and then factorial that result. Here's an example for combinations. Find a way of selecting 2 applicants out of 5, and hence finding the total number of sample points. We want to select 2 applicants with no order. So there's 2 unordered subsets. The total number of applicants is 5, so n equals 5, while r equals 2. According to the combinations calculations, the amount of combinations is 10. So right there on the formula you see C 5, 2. So that should equal 5 factorial over 2 factorial times parentheses 5 minus 2 factorial that, which should equal 10. Before we conclude, I want to highlight the main difference between combinations and permutations. Permutations tend to require some sort of order or ranking in its pairing or grouping, while combinations do not. Thank you for watching my video on counting rules.